Apart from water wastage, our project aims at three things. Street, and I'm part of the think tank team. And today I'm going to explain you how our project is going to work, the basic idea of our project. Okay, so first of all, we've divided our project into three parts. Stage 1, which is the basic prototype. Stage 2, an extended version of the prototype. And Stage 3, entering the market. Now, currently we've developed Stage 1, but we're going to work on how we'll be able to move on to Stage 2. So first of all, I just want to give you a little background on the project. According to Wired magazine, 70% of wasted water is coming from the agricultural sector. Now that's a huge amount. And second, WWF has stated that 2,500 trillion liters of water is being used in the agricultural sector. And out of that, 1,500 trillion liters of water are being wasted. So that's again a huge amount. Now our project, it aims to reduce this amount of water being wasted. From prevention of wastage of water, our project aims at three other things: judicious use of fertilizers, less labor, and less cost. Cost is reduced because again less labor and less water is wasted. Generally, in rural farming, you'll see wastage of water in multiple ways. Now, for example, let's consider this as a field. Motor will be located in one corner of the field, okay? So now let's say that a section here requires water. The motor will be pumping water from here to the entire field. So until water reaches this section, it will not be getting water. And from, let's say it's pumping from here, it'll have to travel through an area of the field that is already got its required amount of water. So basically here we're giving excess amount of water to this entire part of the field, which is again a huge waste. And apart from this, you'll see water being stagnated. Now, if you're growing staple crops like paddy, wheat, and various other crops, in rural farming, what you see is they will construct a little dam type thing across the field, and water will be stagnated. Now, that's all fine, but the problem comes when there are no crops yet being grown. As water is filled up to the brim, it's constantly evaporating. So again, huge amount of water is being wasted by stagnation. And apart from this, in various parts of the season, they'll need to drain this stagnated water. So again, when they're draining this water, huge volumes of water is just being washed out. So again, here, water is again being wasted.
The project.
There are three stages to our project. Stage 1, basic prototype. Stage 2, extended prototype. And Stage 3, entering the market. Now Stage 1 is done. We've completed that. The basic prototype consists of a moisture sensor which is connected to an Arduino. The Arduino is then connected to a transceiver which will then communicate to a solenoid valve. The solenoid valve will open and let water flow if the moisture sensor tells the solenoid that the land is dry. Now, if the land is moist, the solenoid will stop the water and impede the flow. Stage 1 prototype is currently in a lab. We do not have it ready with us right now, but it's built, and we've built it so that we can show investors what we're planning on doing. Now, Stage 2 is a bit more expensive, so we won't be able to do it until we receive the
Stage 2
appropriate funding. Stage 2 consists of two things: a sensor and the grid-based agricultural system. Now this is a sensor for Stage 2. The sensor consists of a glass casing and a plastic casing on top. Basically, the glass part will be underground and this plastic part will be above ground. So there will be 4 electrodes. this shows a front part. So let's take the front two electrodes. The front two electrodes will help in detecting the moisture. Now, if the soil is wet, conduction takes place easier. So with the change in voltage, we'll be able to tell if the soil is moist or not. Back two electrodes will be used to test the fertility of the soil. Now, if the soil is fertile, it'll have a lot of nitrogen and phosphate minerals. So basically, how we detect the nitrogen and phosphate minerals is by a chemical reaction. These nitrate and phosphates will react with the electrodes, causing a change in voltage, which will send a voltage signal to an amplifier. Now this amplifier will amplify the signal, and it'll be able to tell whether the soil has nitrogen and phosphate minerals or not. Let us say that the sensor is rich in minerals. It'll grow green, meaning that the soil is fertile. Now if it's not rich in minerals, it'll grow red, meaning that it's poor in fertilizers. I'd like to point you to the second part of our stage 2 innovation. This is a grid-based agricultural field system. So now basically the sensor, as I told you, has two functions. The first function is to detect the moisture of the soil, and second function is to detect the fertility of the soil. So I'd like to explain first the water distribution. Now let's say that here sensor R3 detects that there is less water in this area. Now it'll communicate to a centralized unit over here, basically a computer, and it'll tell it that there's less water here. So now the motor will pump water through this mother pipe over here and send water through this pipe here. And here a solenoid valve will open, allowing water to flow only over here. Now, as I said, R3 says that it's dry. Now let's say that all the others are saying that it's moist, the soil. So the water is distributed only to R3. Second function of the sensor is to test the fertility of the soil. So now, for example, let's say that in the space surrounding R1 it is fertile, and space surrounding R2 it is not fertile. R1 will send the binary code 1 to the system over here, saying that it's fertile. R2 will send the binary code 0 to the system over here, saying that it's not fertile. Now, again, R1 will be glowing green and R2 will be glowing red. So now the farmer knows that the land here is fertile and the land here is not fertile. So he'll spread fertilizers only to the land in R2. This way he'll be saving the extra fertilizers he'll be spending here. He'll be spending fertilizers only at R2 and various other places that require fertilizers. Stage 2, we will need to build a fully functioning sensor. The sensor I've talked to you about. We're currently building one unit, and it's going underway where it's being welded right now. But to actually fully analyze the field, we'll need about 20 sensors minimum. And each sensor to build from scratch is costing us about around $45. So it's a bit expensive. Stage 2, we're looking for investors currently. We have talked to several investors. They seem interested, and we hope to take it further. Now, testing was again part of stage 2. Now, stage 3 is entering the market. To enter the market, we will need to be setting up a server basically. And in this server, farmers can store their data and have it communicated with other agriculturists and horticulturists. So basically, now let's say if the farmer is in out of town somewhere and he has to access the data of his field, he can take out his smartphone, connect to the server, and check out the data of his farm, a live feed basically. Other than that, he can also share this data to agriculture experts somewhere else, and they'll be able to tell him basically how to progress the growth of his crops. So we're not only constricting ourselves to a final product, we're basically also building a farming community.
Summary.
I'd like to summarize the advantages of our project. Now, first of all, water wastage is reduced. With our grid-based system, we're reducing the wastage of water. Now, apart from this, fertilizer is also used judiciously. Now, in regular farms, you'll see, or rural farms at least, you'll see the farmer just randomly spreading fertilizer. Now, when that happens, he wastes a lot of fertilizer. So apart from that, we're taking a more judicious approach. Apart from this, labor and time is also reduced. Every day, a rural farmer will have to wake up, go all the way to the motor, switch it on, and come back. Apart from this, we're making it so that it can be done automatically. Now, the crop yield is obviously also increasing, and farmer gets live feedback. He can be somewhere far away from his farm and get live feedback from the sensors basically. And also the cost is reduced. The cost is reduced in two ways. Water is being reduced, so the cost spent on water is reduced. And again, fertilizers are being distributed equally. So again, you won't be using excess fertilizer. You're saving costs on fertilizers as well.
Conclusion.
So Shell, I'd like to conclude by telling you the final motto of our project. We aim to build a farming community where farmers can communicate with each other and also take rural farming to the 21st century. Now, before concluding the video, there are some people that we need to thank. First, I'd like to thank our senior Sai Teja for his help in electronics. He's been one of the guiding lights. Ram Subhash for helping us gather all the material required. Akhil Pandey for writing the code for stage 2. Raviteja Soringla for guiding us. Bhaskar Kondaviti for his invaluable advice. And again, I'd like to thank our Shell mentor Abdul Rahman for his guidance. And also, I'd like to express my deepest gratitude for Shell for allowing us to showcase this project to the world. Thank you.
Thank you.